right, good morning. Good enough. So we're going to look at 13.3 today. Continuing building on top of the derivative of vector functions. First thing we're going to look at is the arc length of a vector value function. Again, then we're going to look at this thing called the curvature. All right, so let's start with the arc length. Suppose you got some vector value function, r of t is x, and these are functions of t in general. Okay, x of t, y of t, z of t. And for simplicity, let's say it looks something like that. Now, if you want to know how long that curve is from, let's say, t is equal to a to t is equal to b, let's make b over here. How long is this curve from t is equal to a to t is equal to b? Okay, it's a very practical question. If you can describe the motion of any object, an airplane, for example, as a function of time. You want to know how much distance it has traveled for various reasons from A to B. Right? It's a very practical question. So how do we find this? So one thing we can do, let me resketch this portion of the curve here. This is t is equal to a. This is t is equal to b. One thing I can do is I can cut it in two little pieces for now. Let's say right here. And this is some other time. Let's call that t1. From a to t1, notice that the straight line segment is approximately equal to the curved segment. It's roughly equal to the true arc length from t is equal to a to t is equal to t1. And we know how to calculate this thing right here. If I take the derivative at t is equal to a, this is r prime of a, right? If I take the magnitude of this, multiply the change in time, that will roughly give me the straight segment. Roughly. Okay, so the straight segment, the line segment, has a length that's equal to the magnitude of r prime at whatever value was starting at a there, times the change in time, right? And then what I do is I take the second piece, then add the next segment, and that one is at r prime of t1 times roughly the change in time. So the combination of these two, if you look at the graph I had on the last page, will be roughly equal to the total segment of that curve, the total length of that curve. So the sum is roughly equal to the arc length. Okay, of course, we're not going to be happy with the approximation no matter how good it is. We want the exact length. And you've taken calculus for many years now, so what do you think we can do to make that happen? We can shrink the change in time to a very, very small change in time, right? So we shrink delta t, and when that happens, delta t turns into some differential change in time dt. So some random segment right here, this one is going to have a length of r prime at some value of t of my choice times dt, right? That's the length of that little green segment. The length of the short segment. So again, using the calculus knowledge you already have, if I want the entire thing here, I want a little piece here, a little piece here, 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 all the way to B. How do we accomplish that? How do you accumulate all these little ones together? We integrate. Very good. How do you spell that? Accumulate. We'll call the length L, and we get that by integrating from starting time A to the end time B. And what do we integrate? We integrate these short little segments. Each one has a length of r. That's a prime here, sorry. Very important thing here. That's an r prime, right? You take the derivative, and the length of that will be roughly equal to the straight segment at that point. When we integrate r prime of t times dt. Does that make sense, the reasoning behind this formula? Yeah? Okay, so we're accumulating little stuff to get the total length. So let me write that formula again from A, B, magnitude r prime of t dt. Now if r, like we had earlier, r of t is x of t, y of t, and z of t, r prime, of course, is x prime, y prime, z prime, or dx dt, dy dt, dz dt. So an alternate form of this same formula is to find the length of that. And we know how to find the length of a vector, square root of the sum of squares, right? So this is equal to dx dt squared plus dy dt squared plus dz dt squared, all of that under a radical dt. Okay, so that's a general vector formula here, specifically for the case of a three-dimensional. This formula will give us the length of that arc. Provided that we could differentiate and integrate all of that stuff. And that requirement is very simply met by requiring the curve to be smooth. doable as long as R of t is smooth. The same usual requirement you had for differentiability and integrability of all the functions that you have encountered before. Continuous, derivative always exists, and all that stuff. So in other words, as long as the curve is smooth. All right, so let's try this on something. Let's look at this helix that we have been looking at. R of t is equal to cosine of t, just t, and sine of t. Let's find out how long that helix is if we start accumulating at t equal to 0 and we end at t is equal to 2 pi. Okay, so once again, you've seen this before. We're starting at 0. At 0, the point is 1, 0, 0. So at 0, we're right here. At 2 pi, we're at 1, 2 pi, 0. So y is 2 pi and x is 0, y at z is 0. So somewhere over here, t is 2 pi. And in between, x squared plus z squared is equal to 1. So in the x and z plane, we see a bunch of circles, radius 1, centered at the origin. And y has a t, so that circle is stretched out and growing with y. Okay, so something like that. And you saw this before. We've seen that shape quite a few times now. All right, so from here to here, normally that's not something we can measure unless it's made of a material that you can cut out and then stretch it out and lay a ruler next to it. But we have a way to find out exactly how long it is. Okay, so according to the formula, what we want is from 0 to 2 pi, an integration. The magnitude of the derivative, tangent vector, in other words. R prime, that's very easy to find. Minus sine, positive 1, cosine. Then we integrate the magnitude of that. And the magnitude is equal to sine squared plus 1 squared plus cosine squared under a root okay, and cosine plus sine is 1. 1 plus 1 is 2. So this is radical 2. And therefore, the magnitude at the length, entire, for the segment of that helix we want is 0 to 2 pi, magnitude of r prime. And we get radical 2 times t, 0 to 2 pi, so that's radical, that's 2 radical 2 times pi. Right? Questions? Okay, let's try another one. Let's try this one. R of t is equal to 12ti plus 8t to the 3 halves j plus 3t squared k. And let's find the length from 0 to 1. And there's really nothing to it. You take the derivative, add them together, square them, add them together, integrate. There's really nothing to it. Right? That's all we're doing here. And just remember, there's really no need to remember the formula. Remember the reason where this formula works is that we're adding up little short straight segment defined by the magnitude of the tangent vector times the change in time. All right, so R prime, that's 12. That's 6, is that right? 6t to the 1/2. No, 12. Right? 3 over 2 times 8, that's 12, right? 12. This is 6t. 6t? Okay, that's not too bad. Magnitude of that, this thing squared, that's 144. This thing squared is 144t. This thing squared is 36t squared. And all of that stuff under a radical. Okay, notice this time that this thing is a function of t. Last time, with the helix, r prime of t was not a function of t. That meant r prime of t is constant throughout. And that makes sense because it's a very regular shape. It's a circle that's growing at a very, very regular rate. So the magnitude of the tangent vector doesn't change. Think of a circle. Going around, you always get the same magnitude of the tangent vector. Here we got something different going on. So this is in general a function of time, t. All right, so integrating this, it's 0 to 1. This thing right here, dt. So how do we integrate this? Starting with that, 0, 1. Let's take a 36 out of all of this stuff. It comes out of the root, becomes a 6. And that's a t squared. And 144 divided by 36 is 4, right? And this is a 4. And this is a perfect square, right? 0, 1, 6 times the radical of t plus 2, the quantity squared. And remember, we're integrating the magnitude of a vector. So this is always going to be positive. we take the positive root of this. This is the stuff we're integrating. So this is 0 to 1, 6 times the positive root. And from here, this is trivial. This will be 15 at the end. Should be. Yeah, 15. Make sense? Questions? All right, now we're going to do something a little bit different. And let's revisit a helix. Cosine of t, positive t, sine of t. Now, instead of specifying the end time, A to B, in other words, let's just do t from 0 to some other t at the later time, starting at 0, just like the earlier example we did. Right? We did 0 to 2 pi, and now we're going to leave this 2 pi as a free variable. And at the end, we won't get a constant anymore. We'll get something that's a function of t, right? If I don't specify the end time, then the arc length has to depend on what the end time I put in. So the arc length will be a function of t1, 0 to t1 integration, the magnitude of the derivative. And that we did earlier was radical 2. So at the end, this will be radical 2 times t1. So as you expect, if you don't specify the end time, then of course the end result will be depending on whatever the end time you put in. So here, let's drop that subscript 1 here. We're talking about a sum variable. We can name it whatever we want. Let's leave it just simply as t. And this right here, let's call this thing little s of t. And this now becomes what's called the arc length function. It's not a constant anymore. We're not specifying where we end. If someone tells you to keep driving, doesn't tell you when to stop, and asks you how much distance you have covered, well, of course, it's as long as you're allowed to drive, as long as you can drive, right? So notice here that if you look at this part of the equation, s is equal to radical 2t. I found a relationship between the arc length function as time goes on and the time. This means that I could also rewrite time as a function of the arc length. Normally, you drive on, you say, an hour later I've driven 70 miles, whatever. You can turn that around, right? If you know how fast you're going, someone can say, you've driven 70 miles, how long did it take you? Well, 70 divided by how fast you're going. That's the same idea here. We solve for time as a function of the arc length. So this means I could parameterize my space curve not with t, but with s. So I could rewrite my space curve cosine t sine t as cosine of t s over radical 2 t s over radical 2 and sine of t sine of s over radical 2. So here is the space curve parameterized by the arc length instead of time. Okay? The thing here is once we found out how arc length is related to t, we can choose whatever independent variable we want to parameterize that space curve with. It could be t, a very natural choice, or it could be the length of the curve you have traveled. To make it more concrete here, let's look at these two. The original one with t in there, this is saying that, this is telling you where the object is if given time. So for example, 2 hours later, the object is at where? The object is at wherever, fill in the blank. If you parameterize that with respect to the arc length, then time is not in the picture anymore. You need to tell me how much distance you have moved. So this is saying that after traveling for s amount of distance, the object is at blah. And this is how the odometer in your car is telling you essentially. You take the car off the lot, you've driven that for 10,000 miles. After traveling for 10,000 miles, that's your S right here. You are at wherever you are, right? Now, if you're running on the track, you're timing yourself with time. That's looking at this. After I've run for 20 seconds around the track, I am at halfway around 400-meter track, 20 seconds for me. No, I wouldn't be halfway around the track. It would take me a little bit longer. For you, maybe halfway around, maybe more, but I would be somewhere, right? You see the difference here? One is that you tell me time, I tell you where I am. One is you can tell me after I've moved this much, where I am. Both of these will tell me the same thing, but in order to pinpoint where I am, I need two different kinds of information. And they are related, as we have seen earlier. Okay, now let's talk about this thing called, well, actually, let's just draw a curve here, and then we'll look at the vectors we get out of it. So there's my curve, and at any point, if I take the derivative, then I get a tangent vector. And the important thing to remember is that that vector right here is not a unit vector in general. It depends on how fast the object is traveling. The magnitude of that is the speed of that object, right? So in general, that's not going to be a unit vector. And in many applications, the unit tangent vector is of some usefulness. It tells you the direction that you're going without and factoring out the speed, simply knowing you're traveling in a certain direction. In this book, we use capital T for the unit tangent vector. And you remember, to make any vector a unit vector, you take the vector divided by its magnitude, right? So the tangent vector divided by the magnitude. And so therefore, because it's a unit vector, the magnitude of that, of capital T, the unit tangent vector, is forever 1, always equal to 1. The derivative of T is T prime. Okay? So T prime, this is the rate of change of the unit vector. In other words, it tells you how T is changing as little t time changes. Okay, so let me ask you a question. We know capital T is a unit vector. What about capital T prime? Is it a unit vector? And how do you know? Think about this. Think about this. T, capital T is a unit vector. Is the derivative a unit vector? Let me put it this way. Is it always a unit vector? What do you think? If you're shaking your head, and that means no, then you're right. Now, why is it not a unit vector? Can you give me an example where t is a unit vector, but the derivative is not? Yeah, that's right. Right. So can you give me an example where t is a unit vector, but t prime is not? I can think of 3 examples off the top of my head. Yeah, that's right. How about the ijk vector? Are they unit vectors? Is the derivative of ijk vector any of the ij or k unit vector? What is it? What's the derivative of I? 0, right. So, no, T prime is in general not a unit vector. For example, let T equal to I, right? If you think of a straight line along the x-axis, then the tangent vector is I, yes? And the derivative of I is 0. So the rate of change of T is the derivative of I, and it's a 0. A 0 vector, not a 0 scalar, right? Derivative of a vector is a vector, a 0 vector. So a 0 vector is a vector with all zeros, as you would expect. And T prime and T have a very interesting relationship. So let's say this is my unit tangent vector. T prime tells you how the unit tangent vector is changing. So if you look at this curve right here, as I move through it, my tangent vector is going to have to turn to the right in the first half of this curve. And that means I need some kind of change going into that curve. And in this case, T prime would point this direction. So let me write that down. T prime points into the turn. Okay, if you put your hand out and walk like this, that's your tangent vector. If you turn to the right, then something has to force you to move to the right, and that's the T prime vector. It will move into the turn. So as T goes on here, T prime always points into the turn. So at this portion here, it is still finishing up its right turn. So over here, it would be pointing into here. And here it's starting its left turn now. It'll be pointing into the turn. Okay, does that make sense? How you can find the direction of T prime? If you have the curve, you know, you just look which way the turn is going into, and that points into the turn. And I've drawn all of them perpendicular to T, and that's because T prime is always perpendicular or orthogonal, perpendicular, which is a shorter word, whatever, to T. But remember, T prime is, in general, not a unit vector. If we're talking about unit vector here, it makes sense. For some applications, it's important to also talk about a unit vector in the T prime direction. So let's define what's called a unit normal vector. The word normal in a lot of mathematical contexts means perpendicular. And that's a short word, so maybe we'll use normal a lot. The unit normal vector, capital N is in the same direction as t prime, but to make it a unit vector, we divide it by the magnitude of t prime. And the relationship to always keep in mind is that t is always perpendicular to n. Okay, so now you got the unit vector, unit normal vector, and you have the unit tangent vector. Now notice that on a on a less curvy section, let's say right here, let's use, capital T. On the less curvy section of the space curve, T is not changing too much. So we expect T prime to be a small magnitude vector. T does not change much. So we expect T prime to be small. On a very curvy section, T has to change very drastically within a short amount of time. We expect a much bigger, relative to earlier, much bigger T prime. More curvy section. Magnitude of T prime is larger. And larger in relation to what? In relation to the tangent vector. So the ratio between, let's write that down, in relation to r prime, right? The velocity you're going and how fast you're turning. So by on a straight line segment, r prime will be much, much longer than t prime on a very straight less curvy section. On a curvier section, this will be very big in relation to the tangent vector. The ratio of these two is called a curvature. And this symbol the book uses is a Greek letter kappa, lowercase kappa. It looks like a K because that's where we get K from. No, that's not where we get K from. We get K from the Roman alphabet. But that, anyway, it looks like K, but it's not. It's like a little k, a little tiny little k. So this kappa is defined as the magnitude of the change of the unit tangent vector in relation to the tangent vector. If you're driving a car here, this is measuring how fast you have to turn in relation to how fast you're going at that time. If it's really, really curvy, then this will be a big ratio. Big kappa means curvier space curve. For a line, kappa will be 0. 0 curvature, right? A straight line has no curvature, 0 curvature. All right, so let's finish that with our helix again. Let's find out what the curvature and all that stuff is. Cosine of t, positive t, sine of t. Let's find the unit tangent, the unit normal, and kappa. Okay, the unit tangent is very simple. It's the magnitude of the tangent vector. It's a tangent vector divided by its magnitude. It's how you would make any vector a unit vector. All right, so r prime, this is simple. Negative sine 1, positive cosine. And the magnitude of r prime, we calculated this earlier when we did the arc length. That's where we got that radical 2 from. So we did this earlier. Okay, look back in your notes to find out how we got that. Or simply take the magnitude of that. So this right here this is our unit tangent. This is a tangent vector that's always the vector that's always tangent to the helix and always has a magnitude of 1. Yeah. This is the definition of t, right? So all I did is I took the derivative of this to get that, divided by the magnitude. We're going to do n right now, okay? N, the unit normal. The unit normal, look back 2 pages, is big T prime divided by magnitude of big T prime. The change in the unit vector. So it's related to if you're turning, how the unit tangent is changing. So n is, just had it. T prime, big T prime, divided by magnitude of big T. Oh, nope, I had the wrong. Oh, that's right, never mind. We're fine. All right, so big T is up here. Let's first take the derivative. Derivative of this is negative cosine over radical 2. Derivative of the y component, 0. Derivative of cosine over radical 2 is minus sine over radical 2. Over the magnitude of this. So this square plus that square under square root. Cosine squared of t over 2 plus 0 squared plus sine squared over 2. Right? So this is radical 1 over 2. And if you divide this by radical 1 over 2, it's the same as multiplying by radical 2. So that's minus cosine of t, 0 minus sine of t. Always make sure that this is a unit vector, and it is, right? Okay, the last thing here, kappa, is t prime magnitude over r prime the magnitude, right? And we have all of these things already. T prime magnitude is 1 over radical 2. R prime magnitude is radical 2. So both of these things we had earlier. Dividing this out, we get 1 over 2. It's not 0, so we know it's not a straight line, but we knew that already. But anyway, that's a measure of how curvy that curve is. Okay, sorry I ran 1 minute over. See you on Friday.